So today we're going to look at predicting the products of a reaction. So up until this point, we've been given the reactants and products for a reaction, and then we just have to write it and balance it. But now we know with our reaction types and our understanding of naming and formula writing, we should be able to figure out what type of reaction we're looking at and likely what the products are going to be made. So in this image on your screen, if you're looking at the reaction, let's just say you were just given the two reactants. So AgNO3 and NaCl. Just looking at that, I can see that, or I can think that this is a double replacement reaction because we have a positive ion, negative ion, positive ion, negative ion. So we have two couples and we're going to switch. So Ag on this side is a 1 plus and it's going to end up going with Cl. And then Na is going to switch and go with NO3. So what you end up with, and we use the charges, is AgCl and NaNO3. So we can actually just use those charges and figure out what's likely to be made. So we'll go through the different types of reactions and see if we can't predict the products. How we're going to do this, we're going to look at the type of reaction or figure out what type of reaction we might be given, and then we'll figure out what the products are going to be based on that. We always will use the charges to determine the formula or the other rules of naming that we've done, like Hofbrinkel and those kinds of things. We don't worry about balancing the reaction as we're writing the product. We will balance the reaction at the end. And then once we have the products, then we go back and balance it, like I just said. So we'll go through each reaction type and do an example of predicting a product. So synthesis reactions, they should generally be fairly obvious what's going to be made. Sometimes if we're doing covalence, it's not as easy to understand or to know, but we'll try to keep it pretty simple. So in this question, we have Na and Cl2. So even if I wasn't told this was a synthesis reaction, I would probably assume it was because I have two very simple things being combined. So Na and Cl, we have a metal, we have a non-metal. When they go together, off to the side, I'm going to look up their charges because metals and non-metals will form an ionic bond. So Na is a 1 plus and Cl is a 1 minus. So when I put Na and Cl2 together, they're going to become NaCl. Now, this is the biggest thing that I see students make, or the biggest mistake, is they'll try to balance this by doing that. And you can't do that because of these charges. Sodium and chlorine go together in a 1-to-1 ratio. So their charges dictate the formula, not the other way around. So we need to balance the reaction to match up the number of chlorines on both sides. So I will put a 2 there, which means now I need a 2 there. And now we have our balanced reaction. So make sure that you're putting the charges together the way they're supposed to go together, and then we fix the balancing afterwards. So now decomp, same kind of thing. We're going to decompose things. We're going to start with a single thing, and it's probably going to be breaking down into simpler things, and it should be pretty obvious the things that it'll break up into. So let's talk about potassium oxide, so K2O. If I'm going to break this down, it's going to break down into its two elements, potassium and oxygen. The formula for potassium, when it's all by itself, is just K. But the formula for oxygen, if we think of Hofbrinkel, is O2. So notice, this is the kind of thing I would see a lot of students do. Oh, I'm going to take this apart. So we get K2 and O. Well, it's actually the opposite. It's K and O2 because of the way the formulas should be. So what you're going to end up with is this and this. Now, obviously not balanced, so we go back and we fix the balancing now. So we need 2 oxygens here, which means now I'm going to put a 4 there. Now, sometimes there's certain little rules of thumb. So for example, hydroxides, they like to decompose into oxides and water. So if we're talking about calcium hydroxide, excuse me, calcium hydroxide will decompose into calcium oxide and water. So when I see that, I know Ca is a 2 plus and O is a 2 minus. So this is going to make CaO and water is H2O. So now we got to look back and double check our balancing. We got 1 calcium, 1 calcium. We got 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. So we are balanced. That would be an example of a kind of a common decomposition reaction. Now, single displacement. Now, depending on what your single compound is, or sorry, single element, I guess, is, it will switch with whatever its type is. So what I mean here is, if you're looking at magnesium, magnesium is a metal, so it's going to switch spots with sodium. So magnesium needs to go with chlorine, and sodium goes by itself. So what I'm going to do off to the side is I'm going to figure out the charges on magnesium, which is a 2+, and chlorine, or chloride, which is a 1-. So when I want to put magnesium and chlorine together, it's going to be MgCl2. And then sodium is going to go off on its own, so Na is all by itself, and the formula for sodium is just Na. Now again, notice that I have extra chlorines here. I can't just switch them however I feel like. I have to put them together based on these charges. So in doing so, I need a 2 here to balance the chlorines, and now I need a 2 here to balance the sodiums. This is where you have a positive or metals switching. Now, if you see something like this, again, I'm looking at this as there's kind of this single thing and a couple, but in this case, the chlorine and the bromine are switching spots, because we always want to put metals with nonmetals if we can help it. So off to the side, I'm going to do the same thing. So sodium is always a 1+, and chloride will form a 1-. So when I put Na with Cl, it will be NaCl, and then bromine goes off on its own, so that's Br, but because it's Hofbrinkel, it's Br2. So now we're going to fix our balancing. I need 2 chlorines, so I put 2 there. Now I need 2 sodiums, and that also fixes my bromines. So there is our single displacement reaction. Now, the next, or kind of the last of these types is the double displacement. And basically, whatever you have for your compounds, you're just switching partners. So usually you'll have metal, nonmetal, metal, nonmetal. So we're switching it so that the metals and the nonmetal, like the metals switch their spots, or the nonmetals switch their spots. Basically, this and this are going to switch. Potassium is going to go with bromine, and magnesium is going to go with chlorine. Now, off to the side, I would write down their charges. So you give KCl is actually K+ and Cl-, and MgBr2 is Mg2+ and Br-. So now what we're doing, if you think about it, we're actually putting these guys together, and then we're putting these guys together. We're kind of swapping them out. So if I want to put magnesium and chlorine together, that's going to be MgCl2 because of the charges. And if I'm going to put K with Br, it's going to be KBr, no 2. So notice we got an extra chlorine here, and we lost a bromine here. That's okay. We're going to balance it afterwards. So I need 2 chlorines, so I put a 2 there. Now that gives me 2 Ks, so I put a 2 there, which gives me 2 Brs, and now we have a balanced reaction. Now, combustion reactions should be the easiest of all of them to predict because the products never change. I find that lots of students get confused though. We're always reacting these hydrocarbons, and we're reacting them with oxygen. That's what combustion is all about. You're taking a hydrocarbon and you're reacting with oxygen gas, and you're making always carbon dioxide and water. So all we have to do is memorize these 2 products. So even this reaction will also be the same, CO2 plus H2O. Notice it doesn't matter the reaction, this part, I'm just going to circle it in black here. This part is always the same. It's just this chemical that changes, and it's got to be some sort of a hydrocarbon. So now what I'm going to do is I'm going to go back and balance these. And we learned before that the trick to balancing them is to do them in alphabetical order. So I'm going to start with my carbons. I have 8 carbons here, so I'm going to put an 8 there. That gives me my 8 carbons. Now let's check our hydrogens. We have 18, so I need a 9 there. Now I can already tell that this is going to mess things up because I've got 8 times 2 is 16 oxygens here and 9 more. So that's a total of 25 oxygens. We need to have an even number so we can double a number to get to it. So it doesn't work. So what we're going to do is we're going to go back and we're going to fix this by doubling everything we have. So now that becomes a 2. So now I'm going to change my 8, and that 8 is now a 16. And this 9 now becomes an 18. So this 16 that for oxygens is actually 32, and this 9 is an 18, so this 25 is now 50. So that means to balance the oxygens, I need 50 oxygens on the reactant side, so to get 50, 25 times 2. So there is our balanced reaction. Okay, so same deal with this one. The next one is a combustion of a type of sugar. So balance our carbons first. So I have a 6 here. Hydrogens next, I put a 6 there. So now we're going to check our oxygens. 6 times 2 is 12, and 6 more is a total of 18. Now at this point, when I go back, I already have 6 oxygens here. So now I only need, if I take away 6, now I only need 12 more. So to get to 12, I put a 6 there. And there's our balance reaction. So once you figure out the reaction type, then you can figure out what the products are going to be, use charges if we can, balance the reaction at the end, not while you're writing formulas. You can't force the formula to be what you want it to be. You have to balance the reaction based on it. Every single reaction is balanceable. So if you are trying to balance a reaction and it's not working, it's probably because you may have a formula wrong. There may be some sort of formula wrong or the coefficient or probably a subscript incorrect somewhere in your formula. So that's always a good check, is if you can't balance the reaction, there's probably something going on with it.